So it's my pleasure to introduce Matthew Harrison, Trainor, who's going to speak on coding in structures.
Great. Thank you very much for inviting me to the conference, and it's great to see everyone in person for the first time in a long time. The general philosophy I want to take is we're going to think about information being coded into a structure. And if we have two objects A and B, we're going to think of A as being coded in B if from every copy of B we can recover a copy of A. And here, so we'll take A and B to be different kinds of things over the talk. But the general idea is that the A is some kind of information, and A is intrinsically embedded into B in the sense that it's not just an artifact of the presentation of B that we can recover A, but even as we change the different presentations of B, we can still always recover A. So it's sort of intrinsically coded into B. By recover, right, we're all computability theorists. We're going to generally mean to compute or to enumerate. Right, so you're always going to compute or enumerate a copy of B, A from a copy of B. B is always going to be a countable structure, but we're going to take A to be different things over the course of the talk. And we're going to go from simplest to most complicated. So we're going to start by thinking of A as just a subset of natural numbers. Then we're going to think of it, maybe it could be a family of subsets. Maybe it could be a tree. And then finally, it's going to be just any other structure. So we'll sort of go through those in increasing order of complexity and see how things change as we do that. So starting with natural numbers, right? So we got a set of natural numbers x, which you can think of as essentially the same as a binary string. And we say that it's coded in a structure A if every copy of the structure A computes x, right? And in the sort of general definition on the previous slide, we said that every copy of A should compute a copy of x, right? Here, there's really only one copy of x. It's just a set. So, right, A codes the set. No matter what presentation of A you look at, you always have the information x inside of it. It's more convenient here, it turns out, to talk about enumerations instead of computations. So in general, we'll say that something's CE coded if instead of computing it, you can always enumerate it. And this will just, you'll sort of the natural theorems that you prove are really about CE coding, right? Of course, you code something if and only if you CE code it and you CE code its complement, right? So the first definition can sort of be reduced to the second definition. And then maybe a canonical example just to keep in mind, this is a group. So if you take the integers and you take some set x, and we want to code x into a group. So we could do something like list out all the primes in increasing order, any kind of computable list will do. And then we just say, okay, we'll make one divisible by a prime, depending on whether or not the corresponding index is an x, right? So if you think about this from any copy of this group, you can fix the element 1, look at who it's divisible by, and by doing that, you can enumerate back the set x. This is sort of like a canonical group coding CE coding the set x. Now, there's this very well-known theorem by Knight, which says that CE coding is really nicely behaved, in the sense that anytime a structure CE codes a set, there's a really good structural reason for that to happen, right? So it's not just that it happens to be coded, there's a real structural reason. So the theorem says if a set X is CE coded in a structure A, if and only if there's some tuple in the structure, and there's a computable list of existential formulas so that you can tell whether n is an X by looking at whether the corresponding existential formula holds of this tuple. Right, so once you fix this tuple, or if you think about this is if and only if. So one direction is the hard direction, the other direction is easier. If you have all these formulas, right, then it's really easy to cover X. Because you look at this tuple A, and you start searching for the existential formulas to hold, and when one holds, you enumerate the corresponding thing into X. Right. So the really interesting direction is the other direction, right? And that kind of direction is almost always proved by forcing. So you take some generic copy of the structure and use the fact that it codes X to argue that there's sort of whatever reason it coded X is sort of a reason that every structure codes X. Right. So the point is that there's like an if and only if characterization of the coding in terms of something that's purely structural, right? The coding is something about presentations of A, but that equivalent characterization doesn't talk about presentations at all. It just talks about satisfiability, something structural about A, and it's completely independent of presentation. Equivalently, maybe this is sort of a slightly more complicated way to think of it at first, but it's more intuitive once you wrap your head around it, is to think that something C coded, if and only if X is enumeration reducible to the existential type of some tuple. This is really just rephrasing that. But basically, the existential type is all the existential formulas that are true. And in a sense, the existential types are like the maximal things that are coded by the structure. So of course, if you code something, you code anything simpler. So you code all the things enumeration reducible to your existential types. So just a quick example, or going back to that example of the group, Knight's theorem says that there has to be some formulas around, right? And those formulas we're just saying I is an X if and only if there's some element little x that witnesses that one is divisible by pi, right? And the point is that those formulas on the right, that's a computable listing of formulas. And here, right, if you think in the theorem, we said that there was some existential type that the set X was enumeration reducible to. What's that type here? Well, it's the type of the element 1, right? So 1 is that sort of fixed element that's the type. In general, right, so this is a general case where every copy computes. There's also a uniform version, and if it's uniform, then you don't need that tuple around. That tuple sort of deals with the non-uniformity. So this is sort of quite easy to prove that this characterization of C coding is optimal. So if you look at the sets, like how hard is it to say that X is C coded by A? Well, it's sigma 0,3, and it's sigma 0,3 complete, say is a wage degree. That's saying, right, it's already, it's a nice characterization, but it's sort of the best that you could do. Maybe the more interesting thing, right, to point out is that it is actually sigma 3, right? So it's quite a simple characterization. Whereas if you think about it, right, the naive definition of C coding does something about for every copy of A. But to say for every copy of A, that's a pi11 thing to say, right? So if you think about that, characterization by Knight really brings it down from pi11 to sigma 0,3. Now, why do we care about coding in general? This is going to be sort of a running theme also, is that it's a good way to think about degree spectra. And if you think about how do we ever build examples of degree spectra, it's really by doing some kind of coding. So if you remember, I think we've seen this a couple times, this definition, that the degree spectrum of a structure is all of the sets that can compute a copy of that structure. So coding a set, what does that get you in terms of degree spectrum? Well, it basically gets you the upper cones. And then what you do is you basically pick a structure that minimally codes X, right? It codes X, but it doesn't do anything else. So for example, if you take this group H, so it's C codes X, so if we want to compute X, we need to code X and its complement. But if you take this group for X join X complement, that'll be a structure that every copy computes X, and X can also compute a copy. So if you think of this like it coded X, but it did it in a very minimal way where there's nothing else going on in the structure. So in general, right, if you do some kind of coding in a minimal way, that's basically how we build examples of degree spectra. So that's coding sets, right? And basically the takeaway from coding sets is that it's essentially very well understood, right? We have a good characterization of when a set's coded. It's a very simple characterization, and you actually can't do that much with them in terms of things like degree spectra. But now if we look at families of sets, we're going to get a much richer picture emerging. So what's a family of sets? It's a countable collection of subsets of natural numbers. Right, so you're basically taking the sets from the previous section, and you're taking collections of them. But we want to think about them as unordered collections. So how do you present a family of sets? Basically, you give a listing of all the members, but the listing can be in whatever order you want. So maybe more formally, right, an enumeration of the family is a set of pairs. So you're thinking of this as like a sequence of columns. And the family F should be the set that's all the columns. Right, so this is just you're giving a single list of all the sets in F. And then you'll say that it's computably enumerable from a set X if CE and X, you can build an enumeration. Right, so what this is saying is that X can list out a bunch of sets. And by list out, I mean it can enumerate a bunch of sets uniformly. And those sets are the family. So we're going to think of these enumerations, right? That's what we think of as copies of the family. is lists of the sets in some order. And then, right, so taking that sort of first general definition, we say a family F is C-coded in a structure A if it's computably enumerable from all of the copies of A, right? So this is just adapting our general definition to this situation. Basically, you're thinking, right, every copy of A can list out all of the sets in F in some order, but different copies of A might list out all the sets in a different order. So that's sort of the extra power that we get, right, is this fact that we can change the order in different copies. So probably many people know, right, that there's a ton of really interesting examples in computable structure theory that essentially boil down to building a very interesting family of sets and then coding it into a structure. So maybe the best or most interesting is this one from Slayman and Vayner. So the first thing they proved, I think Slayman did it the opposite direction, but I think Vayner did it this direction, is to prove first that there's a family of finite sets and it can be enumerated by any non-computable degree, but it doesn't have a computable enumeration. Right, so it's sort of this is like a problem. The problem of enumerating this is something that can be solved using any kind of non-computable information at all, but can't be solved with just with computable information. So this is a family, right? And then doing some kind of minimal coding, like with that group, you can turn this into a degree spectrum. So there's a structure that has no computable copy, but any non-computable set can compute a copy. Right? In terms of degree spectrum, the degree spectrum is exactly the non-computable sets. We call this the Slayman-Vayner spectrum. Right? So I think this is a super interesting example, and it shows that there's suddenly a huge jump in terms of what you can do with families of sets versus what you can do just by coding sets themselves. So after we talk about families in sort of a more general context, I'm going to return to talk about some interesting examples of particular families and stuff. But first, I want to do sort of the more general analysis like we did for coding sets. So let's imagine that a family F is CE-coded in a structure A. So what does that mean? Well, that means so every copy of A can enumerate F. And particularly if you're going to enumerate the family F, you're going to have to enumerate every individual set in F. Right? So each of the sets in F is C-coded in A. And by Knight's theorem, that means that each of them has a tuple, and there's these set of formulas, right, for that particular set. So right, the particular set is enumeration reducible to the existential of that tuple by some enumeration operator, theta. But the tuple, right, for each of these sets, the tuple might be different. The operator might be different. Some tuples might not be the tuple corresponding to anything, right? So sort of each of them individually can be found somewhere in an existential type. If you wanted to enumerate the whole family, you have to figure out how do you put each of those individual things together and even decide which ones you're going to pick. Right? So that's sort of the problem of enumerating families beyond enumerating a set. So let's think of like what would the natural way to enumerate a family be in this sort of definability sense? Let's fix a enumeration of all the enumeration operators, just a list of them. So what you might imagine is that, right, like the most natural way to code a family is basically that you have some way of picking out what those tuples are and what those enumerations are. So there's a list of computable sigma 1 formulas, and it should be a computable list. And you should think of those formulas as picking out those tuples that are going to be the ones that enumerate a particular set. Right? So the phi L is going to pick out tuples for which we're going to use the ELF enumeration operator. Right? And so because the phi's are sigma 1, you can look through the structure and you can recognize all of those tuples that they pick out. You can list out all the tuples they pick out. And then for each tuple that gets picked out, you apply the operator to the existential type, and that enumerates a particular set. Right, so this gives a way of looking for a bunch of tuples. Each tuple enumerates a set. And maybe the family is going to be equal to this. Right? So definitely the thing on the right-hand side, that's going to be a way of enumerating a family from every copy of the structure. And the most natural way for F to be C-coded would be for it to be equal to something that comes of this form. So you should think of this as like the family version of what Knight's theorem for sets would generalize to. Right? This is, if it was going to generalize, this is what it should be. What's the best that we know? That we can get sigma 3 formulas here. So this isn't going to give you an if and only if condition, right? If this top thing happens, then definitely F is CE coded. And if F is CE coded, then there's these sigma 3 formulas that do this. So that's sort of an implication, and it never wraps around. Right. So this says if you are CE coded, then there is some way of seeing that you are. But right, this way doesn't pick out a list of the tuples. It gives you some way of approximating the tuples that you were supposed to use. So it doesn't give you if and only if. So natural question, right, is can you strengthen sigma 3 to sigma 1, right? Which is basically, can you get an if and only if characterization of a structural property for coding a family? And the answer is no. So there's some structure, and there's a particular family that's coded in that structure, but there's no uniformly computable list of sigma 1 formulas that make this happen. All right, so basically this structure in this family, there's and more generally, there's sort of a stronger version of the theorem that more generally you can sort of see that there's no real good structural way of seeing why the family is coded. So you think that for sets, right, anytime a set is coded, there's a really good structural reason. But a family can be coded without a really good structural reason. Still open, I don't know if you can make the formulas sigma 2, right? Antonio showed that it can be sigma 3. They can't be sigma 1. We're not sure about sigma 2. Maybe an even better way of arguing that there's no good structural characterization is to look at the wage degree of the set, right? So the families being coded by A, how complicated is it to tell whether that's true or not? And you can show that that has pi11 complete wage degree, which is what the naive definition is, right? What's the naive definition of coding? It says for every copy of A, there's some operator that enumerates F. That's a pi11 naive statement. And so basically what this is saying is that the only way to tell whether a family is coded by a structure is to basically just check the naive definition, right? So comparing to coding by sets, right? Coding by sets that was sigma 3, you can tell whether a set's coded in a very nice arithmetic way. For a family, there's no good way to tell it. So essentially, some families sort of just happen to get coded by the structure, and you can't really tell why. It just so happens that in every copy of the structure, it happens to enumerate the family. But there's no reason more than that's going on. Right, of course, this implies the previous term also, because if there were sigma 1 formulas, then you would get an arithmetic characterization. And yeah, so there's basically the naive definition of coding a family is the best possible one. Now, that's not how things happen in sort of everyday, like when we build things in our natural course of mathematics, we don't build things that are that complicated. We build things that are nicer in a sense, that are CE coded in a kind of stronger way. And we're going to call this the functorially CE coded. So what does this mean? So CE coded means from every copy, you compute an enumeration. So you have different copies that compute different enumerations. And what should happen is if you have an isomorphism between two different copies of the structure, you should get essentially what's an isomorphism between two different copies of the enumerations. What's an isomorphism of families? It's just a rearrangement of the sets, right? So from any two copies, you compute enumerations. From an isomorphism, you can figure out the permutation that rearranges the family into the other family. And moreover, most of the time, it ends up being functorial, right? So if you have like three things, and you have the isomorphism, then the rearrangement from this one to this one is the composition of those two, and so on. So most, I don't want to claim all, but I think maybe all examples of CE-coded families that arise naturally end up being functorially CE-coded. And in this case, you can get a nice characterization, right? You can get this characterization with the sigma 1 formulas. So, right, basically what you should think of it is if the way that something's coded is nice and that it sort of behaves nicely with respect to isomorphism between different copies, then there has to be a really good structural reason for the family to be coded. And if you count the quantifiers here, this is a sigma 5 property, right? So much simpler than pi11. So maybe the moral here, right, is that when things are coded in ways that behave nicely, you can come up with good structural characterizations. When things are coded in some arbitrary way, sometimes there's no good reason why that happened. OK, so I promised to have more interesting examples of families, just to sort of argue to you that a lot of computability theory really does happen just with families. So for example, there's this well-known theorem of Goncharov. So there's a family of sets, and it has exactly 2 different enumerations up to computable equivalent. Right? So computable equivalence is just a computable rearrangement of the family. And if you code that into a structure, right, you basically build a structure that is essentially this family. That tells you there's a computable structure with computable dimension 2. This means it has exactly 2 computable copies up to computable isomorphism. Right? So 2 computable copies, not computably isomorphic to each other, but every other copy is isomorphic to one of those 2. So that's like a really interesting classical example. Right? And it's really all about the families here. Another example I really like is this one of Ramanov and Kalimullin, which says, so there was the Slayman-Weiner structure, right? It had the degree spectrum, which was all the non-computable things. And they showed that you can get this degree spectrum, but not in a uniform way. So what this means is there's no way to get from an X computable set to get an X computable copy of the structure. And the non-uniformity really comes from this sort of cool fact that, so if you have a non-computable set and you view it as a binary expansion, right? So you view zeros and ones, and you think of that as binary expansion of like behind the decimal number. Because it's not a computable set, it's not going to be a computable like real number. So it's not going to be left C or it's not going to be right C, one of the 2. But it might not be either, right? It might be neither left C nor right C, but definitely one of the 2 it's not going to be. And if it's not left C, there's one procedure that they use. And if it's not right C, there's another procedure that they use. But you can't tell which side you should be in. Right? So no matter what, one of those works, but you never know which procedure is going to work. Another interesting thing is to ask whether things in particular classes can code families, right? Or do things of certain kinds. So right, can something in a particular class have the Slayman-Weiner degree spectrum? And maybe the oldest open question here is whether there's a linear order that has Slayman-Weiner degree spectrum. So I think this has been open for, I want to say definitely at least 20, maybe 30 or 40 years. And I think there's sort of more progress than this a little bit, but essentially the best progress plus a little is by Russell Miller. We showed that within the delta 2 degrees, you can get the Slayman-Weiner spectrum, but then other things might happen outside of the delta 2 degrees. I think there's been like no progress on this for a long time. More recently than that, people asked about torsion-free abelian groups. Right? So is there a torsion-free abelian group with the Slayman-Weiner spectrum? And recently, there's this proof announced that torsion-free abelian groups are Borel complete. And if you take a bunch of ideas from that, you can show that there is a torsion-free abelian group that has the Slayman-Weiner spectrum. Right? So it's using sort of these cool new methods from that proof. I put a star here because I haven't completely written down the proof. So I don't want to like absolutely 100% claim it, but I'm pretty sure this is true. Then there's another question that I quite like, which originally I formulated to try to help you with the previous one. But I think it's independently interesting in its own right. And it's sort of it's a natural question by itself. So the Slayman-Weiner spectrum is everything in that is finite. And it really uses that finiteness in a very strong way. So what I asked is there a family F, which is closed under finite differences, right? So if you have a set in the family, then any other set that's only a finite change from that should also be in the family, which has the Slayman-Weiner spectrum, right? So it has no computable enumeration, but you can always enumerate it from any non-computable thing. The motivation with the groups, which turns out not to be necessary for any reason, is that if you look at the divisibility relation in a group, this is in a sense closed under finite differences. Because if, for example, if you have an element X which is not divisible by 2, then 2X is divisible by 2. You can sort of, you look at the divisibilities of some element, there's some other element that looks the same up to some finite chain. So what we showed with Noam and Joe and Dan Turetsky is that you can't do this uniformly. So if you've got a family F, right, closed under finite differences, and from any non-computable set, you can uniformly enumerate a copy of the family, then it's got to have a computable enumeration. Right, so you can't uniformly have the Slayman-Wiener spectrum, but we still don't know if you can do it non-uniformly. Right, so that question is still open. Maybe the best progress towards the other side, there's some stuff that we proved and also some stuff that Fez Ramanov proved. That sort of certain obvious strategies to strengthen this to non-uniform aren't going to work. So for example, he proved that you can have Slayman-Wiener spectrum if you restrict to the CE degrees. So you can be computed from every non-computable CE degree, but not have a computable enumeration, right? Or for example, we showed that for any, I think it was like for any particular set, you can be under that set, but not computable. So it has to be, if this is impossible to do in a non-uniform way, the argument has to look at a lot of different degrees and be a very wide argument. All right. So I think hopefully I sort of convinced you that families are interesting and that they sort of build a whole bunch of interesting examples in computable structure theory, and that families are sort of significantly more complicated to code than just purely sets are. So what's the next step up? Is to think about trees, I think. And first, I want to argue to you that trees really are a generalization of the previous two things. So the first thing I want to argue is that if you've got a set, that you can easily make a tree where the tree really represents the set. If I've got a set W here, for example, 1, 2, and 5, I can make a tree that really represents this set in a sense that like building a copy of the tree is the same as computing the set. And so I just do it like this, right? For each thing in the set, I have a separate node at the bottom, and then it's got some number, and I just go up that many times and then make a split. Right, so obviously, if I have a copy of W, I can compute a copy of this tree. And if I have a copy of this tree, then I just look at all of those first level things. I see how far do they go up until I see a split, and I count that, and that's the number I enumerate. Right, so essentially, building a copy of this tree and building a copy of this set are really the same thing. So trees, sort of coding a tree generalizes coding a set. What about families? Well, you basically can split, right? So the family has a bunch of things in it, W1, W2, and so on. And so you just make a node at the first level for each of those sets. And then you do that same thing we did on the previous slide, right? Coding that particular set into a tree above there. And the point is that the tree doesn't have an ordering on that first level, just like the family doesn't have an ordering on the set. So coding a family of sets and coding a particular tree, right? Those are the same thing. So for any family of sets, there's a tree that coding is the same. Trees generalize coding families. But there's more that people want to do in computable structure theory than just coding families. So for example, if you do something with marker extensions, you can get all sorts of other things. So for example, for every alpha, there's a structure whose degree spectrum is non-low alpha. And how do you do this? Well, you take the Slayman-Wiener spectrum, you relativize it up high, and then you take a marker extension to sort of bump it down and get non-low. How do you do a marker extension? Essentially, a marker extension is looking at like a family, depending on how far you're doing it, you're looking at families of families of families. If alpha is a finite number, then there's some finite number of nested families. But if it's an ordinal, then you've got some ordinal length nested family. Right? So you've got families of families of families and so on. Or you could even, right? So you could even get a degree spectrum, which is the non-hyperarithmetic degrees. And what they do here is they take marker extensions along non-well-founded linear orders. And what that ends up being is families of families of families, but it's not well-founded. You can have like infinite depth nesting of families and families. So one thing we could do, right, we could think about coding like families of families and families of families of families and so on. But I think a really good way of thinking about this is just to think about trees, right? Because if you have families of families of families, you can just think, oh, there's a tree that codes that. In the same sort of building up on the way that we coded a family, right? You can have sort of, it's families of families, you have, those are represented at the first level. There are families in those families are represented at the second level, and then you do something above that. So I want to think about trees as really generalizing all of these kinds of things. So, okay, what do we mean by coding a tree? Or more generally, right, a tree is a structure. So maybe it makes sense now to just hop to what it means to code a structure. So I'm going to say a structure is coded in, which is classically called Muchnick reducible to. A structure B, if from every copy of B, you can compute a copy of A. In terms of degree spectrum, right, if every copy of B computes a copy of A, then the degree spectrum of B is contained in the degree spectrum of A. And that's exactly the same thing. And then, of course, right, maybe I have to put the uniform notion, which is Medvedev reducible, which means that there's a uniform procedure which from every copy of B is going to compute a copy of A. Right. So this is right in the sort of general framework we're thinking of. We might call this coding, but maybe it's better to use the classical terms of Muchnick reducible. Okay, so coding families was more powerful than coding sets. And coding trees is more powerful than coding families, right? Because trees cover families of families and so on. So it's natural to ask, is coding an arbitrary structure more powerful than coding trees? Right, so is there anything that you can code, any kind of maybe, right, anything that you can code in a way with an arbitrary structure that you couldn't have done by using the coding of a tree? And maybe a good way to think about that is to think about degree spectra. All right, so if coding trees and coding structures was the same thing, then any degree spectrum of any structure should be the degree spectrum of a tree. All right, if coding them was equivalent, then any way of coding the one and the other, you get the same degree spectrum. Now, if you sort of look at all the examples of degree spectra, as far as I can see, they're all degree spectra of some tree. Right, that's essentially the constructions that people always use for degree spectra. So that's why this is open, right? Is none of the existing examples are things that will work. And so I think this is a really interesting question because, right, if the answer is yes, then that's super interesting. It says that anything you could do with a tree, which is a much more restricted kind of structure. If the answer is no, that's also interesting because how would you have shown it's no? Well, you would have built some kind of degree spectrum in a way that we've never built a degree spectrum before. Right? So you've built some kind of new technique for degree spectra. So I think either answer to this question is very interesting to me. Now, when you ask a question, right, you should always think, what is like the obvious way to try to prove it? And if it's an interesting question, right, like it would be bad if I put this question up and there was some obvious way to attempt it and that way work. So what's the obvious way to try to prove this? Well, if you know about trees, they're Borel complete. All right, so this is Friedman-Stanley. What does that mean? It means there's a Borel operator. Actually, this one it's a computable operator that for any language L, if you have there's an operator that takes L structures to trees, right? So it turns graphs into trees or whatever kind of structure you want, and it maintains isomorphism. So two structures are isomorphic if and only if the trees you built out of them are isomorphic. Okay, what does this operator do? Essentially, what it does is build something we call the tree of tuples of a structure. So what is the tree of tuples? It's a labeled tree that has all the tuples of A ordered by inclusion. So maybe it's easiest to draw a little picture here. So if you think of the structure A, maybe has like A1, A2, and so on in it. So the tree we're going to build, can you guys see this? So it's got a root node, and the children of the root are all the individual one tuples, and so on. And their children are the two tuples that extend them. Right? So extending A1, you've got, for example, A1, A2, got A1, A3, right, and so on. All the two tuples extending that. Here you've got, for example, A3, A1. Then extending those are the three tuples, and so on. So you're putting all the tuples in the tree ordered by extension. And then what I want to do is I want to label each of the tuples by its atomic type. Right, so maybe I think of that as like there's a color for each atomic type, and I color each thing with what its atomic type is. So if this was a graph, right, then there's an edge relation. Maybe these guys are related, so I color them one color. These guys are not related, so I color them a different color. Right, these guys are related, so I color them one color, and so on. And then for the three types, right, the three tuples is like 8 colors, right, for all the different possible edge relations between those things. So that's the tree of tuples, is it really like takes the structure and spreads it out into a tree. And it's not just a tree, right? It's a labeled tree. So the labels are important, because if I don't have the labels, then it's the same tree for any structure. The labels are what makes it reflect the structure. And then the standard back and forth argument is going to show, right? Obviously, you have 2 isomorphic things. The tree you're going to build is going to be isomorphic, but it goes backwards too. That if these trees are isomorphic, then the original structures were isomorphic. So maybe it's helpful to just sort of think about what does the back and forth argument do. So you got these 2 structures and they're 2 trees. And we're going to assume the 2 trees are isomorphic. We want to build an isomorphism between the structures. So right, back and forth says, okay, we have to take A1 from A. Who's it going to map to in B? Well, the trees are isomorphic. So this one tuple corresponding to A maps to someone over there, like B3, right, in the tree. So then that means that they have to have the same labels, right? So as atomic types, they're the same. So we can map A1 to B3, and that's a partial isomorphism. Then we say, okay, now we need to map B1 needs to come from somewhere. What we're going to do is we're going to look at the tuple B3, B1, and see where that maps to. Right, so that maps to something, and it has to map to something extending A1. It maps to something like A1, A2. And then we say, okay, B1 came from A2. Right, and basically what we do is we do the back and forth construction along a path through this tree of tuples. So the point is that I guess you can think of the tree as being the back and forth information of the structure. Right, it's enough to do any kind of back and forth argument. Okay, so it builds a labeled tree, right? Technically, we need a tree. So, but it's not hard to turn a labeled tree into just a tree. So say we have a tree like this, right? So it's a recursive kind of construction. We have a tree and it's got all these subtrees, T1, T2, and T3, and it's got some label, right? So the root there has some label S. So what we're going to do is we're just going to recursively do whatever this procedure is to all those subtrees over on the right-hand side. And then we need to do something that says we have the label. So we're going to go on the left and we're going to split, right? That split lets us recognize that like that one is the left one, right, as opposed to all the other ones. And then we're just going to go up S times, so we count that, and then we have another split to say we're done. We're just sort of doing the same thing as when we coded sets to put those labels into the tree as things we can recognize. Right, so I want to sort of think of labeled trees and trees as really the same thing. So I might say tree, and really I mean labeled tree from now on. Just turned off. Yeah, I guess. I don't know. Didn't see anything before it turned off. Sorry, the computer's turned off here somehow. I think the first topic was. Yes.
That is not recorded.
So the recording is of this computer. So there is. Yeah, but.
Yeah, it'd be in the download still. Yeah, that's it.
Okay, so. No, don't have.
All right. All right. Okay, so the point is that so there's a computable operator, right, that takes L structures to trees, and that operator is essentially you take this back and forth tree, and then you take away the labels and turn it into a tree, right? So that last step is sort of negligible. Really, it's just taking this tree of tuples. So what does this say? This says that the degree spectrum of A is always contained, right? Because it's a computable operator T, the degree spectrum of A is always contained in the degree spectrum of the tree of tuples. So if you wanted equality, right, what you should know is that every copy of the tree of tuples can recompute a copy of the structure. If you could do that, then the degree spectrum would be equal. But that's false. So what we showed is that there's some structure A, and A's got no computable copies. But if you take the tree of tuples, then that tree does have a computable copy. I think this is really interesting, not just for sort of the things on the last slide, but in general. Essentially what it says is that a structure can't be computably recovered from its back and forth information. So if you have all the back and forth information of the structure from the tree, you still can't build a copy of the structure. And what's going wrong is essentially that if you think of a path through the tree of tuples, right, like a path through here is going to build you a copy of the structure. If you manage to hit every element along the way, right, it'll definitely get you a substructure always, right, because there's no repetition on these tuples. The path is always going to get a substructure. But to get the whole structure, you have to hit everything. So for example, if you have a sufficiently generic path, then it's going to hit everything, and you're going to recover the structure. But you might not be able to get everything in a computable way, right? It might be, if you write down sort of the natural one, then you can see how A was embedded in here, right? Like the leftmost path is just the listing of A in order. But if you make A non-computable, you can still have this sort of shuffle around and become computable, but you can't really see how A sits inside of it. So in particular, right, A and its tree of tuples don't always have the same degree spectrum. So we haven't shown, right, that there's a degree spectrum. We've shown that this particular way doesn't work. We haven't shown that there's a degree spectrum which is not the degree spectrum of a tree. Because it could be that there's some other tree, right, that didn't come from this back and forth tree that has the same degree spectrum. But in some sense, the back and forth tree is like the really natural one to try. And so it's really hard to imagine that there's some other tree out there that can do better than it. Although it's like completely possible, right? There could be some weird reason that a whole bunch of other trees work for some degree spectrum, but the sort of natural one doesn't. But maybe this should be taken as like evidence that it's not the case. Using marker extensions, you can get a strengthening of this. So you can get it to push it up sort of to any level alpha. So there's a structure with no delta alpha computable copies, but the tree of tuples has a computable copy. So you can basically get whatever distance you want between the structure and the tree, you can achieve that. It's not just that you can't compute the structure from the tree, you can't do it with any fixed number of jump. This is kind of similar to something that Knight and Soskova and Vata have proved independently, which is that basically you can't recover A from the tree using an infinitary interpretation. So there's no interpretation of A in its tree. And this follows from this because if you could interpret it, there'd be certain formulas, and that would give you a way to recover it with some number of jumps. Okay, so one thing we did before was we did these complexity calculations for things, right? We said, how complicated is it for this object to be coded in this structure? So here we can ask a similar question, which is, what's the wage degree of the set of pairs of structures A and B, where A is Muchnik reducible to B, right? And a similar question for Medvedev reducibility. So I don't know the answer to this. I have a guess, which is, so you might think at first that it's like pi 1, 2, because that's what it looks like naively. If you think a bit, you'll see it's actually definitely delta 1, 2. But then if you think about the sort of Scott analysis, it's actually going to be at the level of the double hyperjump. Because the fact that any two structures have a Borel isomorphism comes into play here. So the sort of, yeah, I'd say the natural candidate, right, the best upper bound I can find is the double hyperjump, and particularly sort of pi 1, 1 relative to O. the best I know so far, so this is not really a real theorem. It just comes from like the coding of families, is that it's definitely both pi11 hard and sigma11 hard. But at the very least, it's more complicated than coding families. That's, I think, an interesting question. There's also maybe some slight reason to believe that that actually getting the reduction, right, the wage reduction, is going to depend on some determinacy, right? Like maybe the existence of 0 sharp. Right, it's definitely, this is not Borel, so you're not guaranteed that any wage reduction actually exists. And there's some reason to think that maybe you have to use some theoretic assumptions. Okay, so with families, right, there's this general picture that was very complicated. But then if the family was coded in a very nice way, then you got something simpler going on. You actually got the characterization you wanted. And something similar is true for coding structures. So what is like a nice coding of one structure and another structure? It's something functorial again. So this is something that we called a computable functor. And I won't put the full definition because it's like a full page. But essentially what we mean is that from every copy of B, you can compute the copy of A uniformly, right? So different copies of B, different copies of A, but the same reduction. And it's functorial in the sense that from the isomorphism between 2 copies of B, you compute the isomorphism between the 2 copies of A. And functorial in the sense that it respects compositions and things like this. So I would say it's not true anymore that every natural example of coding of a structure and another structure is functorial, right? So for example, a structure is not coded functorial in its back and forth tree. But lots of things are functorial, not everything. And if something is functorially coded, then again, there's some kind of nice characterization. So if it's functorially coded, right, if A is functorially encoded in B, so every copy of B computes a copy of A, then there's a syntactic reason again, which is that A is interpretable in B using computable sigma-1 formulas. So again, what it means to be interpretable is a complicated definition. But if you know the model theoretic definition, you basically take that, but you allow all the formulas to be infinitary sigma-1 formula. And how hard is it to check this, right? What's the complexity of the pairs A and B? The A is functorially coded in B. It's sigma-1,1 now. Right, so that's definitely simpler. We don't know what complexity the arbitrary case is, but this is definitely simpler than that was. Right, so again, if things are coded in some nice way where there's some kind of dynamic niceness, then the characterization is a better one. Okay, so summary. What's the takeaway? Is that there's these 4 things we kind of think of coding. And in terms of coding power, right, structures are at least as powerful as trees. So that's sort of this interesting question of whether structures and trees are the same power or whether structures are more powerful. And then trees are definitely more powerful than families, and families are more powerful than sets. And sort of most computable structure theory happens in trees and families and sets. So I think there's something really interesting here to maybe, right, if structures and trees are different in power, what kinds of things can you explore in that sort of area between the two? Right, that's sort of things that we haven't looked at that much in computable structure theory, maybe. Then the more powerful the coding method is, right, the more complicated it can be to see why it works, right? We wanted these reasons for something to be coded. And for sets, there was always a reason, right? And then the more powerful the method, the harder it was to see that there was a reason. Up to, right, for structures, maybe the double hyperjump even. And then the last thing is that you've got some kind of natural or functorial coding, right? It's simpler than codings in general in the sense that there is always a good reason for things to happen. All right, thank you.
Thanks for the great talk, Matthew. Any questions? Hold on a second, I'll just bring in the mic.
Thanks for a great talk. Suppose you have a structure A and some relation or set, right? And that in every copy B of the structure A, you can compute the image of the relation in this structure B, right? In this copy.
Yeah.
Does this notion like fits in some of those methods of coding structures or sets or families, or it's kind of a different?
I guess that's sort of different because the thing you're computing always changes. I mean, it's sort of related and different, right? So different in the sense that the thing you're computing changes depending on the copy of the structure. But there is a characterization like the night one for sets that says that if this is always, right, if this is called like relatively intrinsically computable relation, right? And so then there always, in that case, is a formula. There's this interesting case where you don't pick a particular relation, but you pick like a family of relations. So you want to compute some member of a class. And there are some really interesting things happen where things get more complicated. So maybe that's sort of things get more complicated there, right? As you look at sets of like family, picking a member of a family in that case, right? Then there's not always a good characterization, I think.
Iskandor, do you want to ask a question?
Thank you, Matthew. So you understand under tree is just a graph with one relation, yes?
Or it's got a like an operator, right? So I guess. Oh yeah. So just there's the relation, but then it's labeled, right? So it's got these relations for labels also.
But the labels, you can reduce the labels into the.
But yeah, you can put them into the tree. So it really is just like the tree.
Yeah, but we know that the structures in general are just graphs. Yeah, so we have some gap between trees and the graphs.
Yeah. So the question is like maybe it could be possible that every degree spectrum of a graph is also the degree spectrum of a tree.
Yeah. Okay.
Yeah. So there's like
And I do not know. Maybe there are some hierarchies of the graphs. I do not know which goes. So you know that tree is just a graph without cycle. Yeah. So I do not know. So it is okay.
Maybe one good way to think of the difference is trees have very specific automorphism group, right?
Yeah.
Like if in a tree, if you can move things around, then you can move them in any permutation, which is like very different from graphs.
Yeah. Okay. Thanks for clarifying.
Sorry, another little question. So you posed an open question whether every spectrum is a spectrum of the tree.
Yeah.
And then you explained that the trees are Borel complete. That's why maybe the answer is yes. So if the answer is still not so, I understood so that the degree spectrum, which is not the degree spectrum of the tree, should be in some case creative. So it should be looked strange at least. So,
Yeah, so maybe you should think of it the other way, Rich, is that this is maybe evidence the answer is no, right? That there is a degree spectrum that's not the degree spectrum of a tree. Because the natural way of trying to build one doesn't work. And so as you say, then the counterexample would have to be very weird.
I mean,
Right.
so if we suppose the existence of the counterexample, what's your intuition how this counterexample should look like?
I really have no idea, right? Because this is like so I think that's the thing, right? Is that this sort of says that we have no idea what a counterexample should look like. Because this is what it should look like, I guess.
Okay.
And then once this is done, I have no idea.
Other questions?
For the Pi11 completeness for the coding sets of families, I was wondering if there's a useful Pi11 rank to think about that relation.
I mean, it's basically about the isomorphism, right? You're just looking at all the copies and seeing whether they code it or not. I guess it's the rank of finding isomorphisms to a thing that doesn't code it. Right, like you're trying to build an isomorphic copy that doesn't code it. And there's like a rank involved in the tree of things that don't code it, I guess, right? That are isomorphic.
Okay, more questions in person or online? If not, let's thank Matthew again for an outstanding talk. I think there's coffee break.